It's my pleasure. First, I just want to welcome everybody to the CASA Moon Survey Planetary Sample Science Seminar Series. And we have a real treat today. Dr. Marina Martinez, a former UNM student who is now in Barcelona and is a postdoctoral research fellow there, will be giving her insights with regards to the sub-microstructures and apatite and its implications for the petrogenetic history of planetary bodies. Marina, it's all yours.
Thank you, Chip. Thanks everybody for being here. Let's see if I can pass the slides. Yes. So why we study apatite microstructures? So apatite is an important host of volatiles, and it's used as a tracer for reconstructing petrogenetic processes in different planetary bodies, including the Moon, the Earth, Mars, and primitive asteroids. And so apatite is important for understanding the volatiles on different planetary bodies. And constraining potential volatile reservoirs is also important for understanding the magmatic and atmospheric evolution of a planet. For example, volatile elements affect mineral stabilities, they control the density and viscosity of magmas, and they determine the type of eruptive processes. However, the formation of apatite is very complex and can result from a range of different processes, from primary magmatic crystallization to secondary processes involving fluids. Only recently, there has been a number of studies dedicated to understand apatite microstructures. And so, because microstructures are usually a function of the formation mechanism, they can be very useful. And the idea is that some microstructures of apatite are potential indicators of the conditions of crystallization, precipitation, fluid interaction of a magmatic source, and subsequent alteration processes. So just to go over a bit of the structure of apatite, I'm sure everybody is familiar with it, but just in case, apatite crystallizes in the hexagonal crystal system, space group P63/M. Here's the formula. And so there's basically three different polyhedra. We have the PO4 tetrahedra, which is rigid and quite invariant. Then we have the calcium 109 polyhedra, which experience little response to the halogen substitution, but recent studies have also demonstrated that that can change. And then we have the one that changes the most, which is the calcium 205XO polyhedra, because this calcium is bonded to the halogens. So there's a huge difference between the sizes of fluorine and chlorine. Fluorine, it's much smaller and fits well, because we have to take into account here that fluoride, chloride, and OH ions are located inside the channels that create the arrangement of planar triangles of calcium 2 atoms at Z14 and Z3/4. So by the hexagonal screw that's perpendicular to the Z-axis. So fluorine fits well into these channels exactly at the mirror plane. However, when chlorine enters into the structure, it's too big, and then different arrangements of these polyhedra occur. I'm going to detail a little bit later. But basically what I wanted to show here is that there has been many studies. I don't want to go into the details of every study, but I just wanted to highlight the contribution that these studies did on understanding apatite structure. Since Hooke's 1989, who predicted that the halogens are not miscible, Ferraris et al. Showed for the first time an exsolution phenomena, where he showed there were different domains for fluorine and chlorine into the structure, and they also showed that there were, even at a smaller scale, elastadite domains that were coherent within the host apatite. McCabe et al. 2008 did experiments with fluorine-chlorine pure apatite, where they show the presence of short-range monoclinic domains, and they suggest that there's a possible solubility of binary fluorine-chlorine apatite. Shedler et al. 2011 also showed that calcium-2 splits in two sides when chlorine enters into the structure, one for fluorine and one for chlorine. And then McCabe and Ustunisik 2018 did apatite melt partition experiments to assess the effects of non-ideal mixing of apatite, and they highlight the importance in vacancies for precluding a miscibility gap. Lee and Costa 2020 also showed there's a stronger non-ideality mixing along the fluorine-chlorine joint compared to fluorine-OH or chlorine-OH joints, and that at magmatic temperature above 800 degrees Celsius, there's no miscibility gap. And finally, a more recent study by Hasran and Tao 2022 showed that although chlorine ions are larger, the fact that they expand the calcium-2 triangles, that makes the calcium-1 contracts, the calcium polyhedra contracts to charge balance oxygens, and so the C-unit cell for fluorine apatite is larger than chlorine apatite, which is a bit counterintuitive. So after that, what I want to show in my talk is our discoveries in apatite microstructures since my dissertation at UNM to my postdoc now at Universitat Autònoma de Barcelona, where I have been looking at apatites from different planetary bodies. So I will show that we found nanoscale exsolution domains of fluorine and chlorine due to unmixing of halogens. We'll show a melt inclusion in apatite with chloroamphibole in an aclite. I will also show an epitaxial fluorapatite vein plus a silica-rich phase at the core of a vein in Northwest Africa 998. All these first time observed in an apatite at these scales. Then we shed new light into the Chassignites-Nacklides magmatic plumbing system. We had additional proof that the magma from which Nacklides crystallized was chlorine-rich compared to the Chassignites, and that chlorine-rich amphiboles in the Nacklides can form without the presence of a fluid phase. Then I will also show multi-phase melt inclusions as perfectly euhedral negative crystals in terrestrial apatite that record melt immiscibility. So let's go ahead with Martian apatites, because many of these observations are in Nacklides, in Martian apatites. I will go over with a little bit of an introduction of Martian Nacklides. Here we have a drawing that's not to scale, but Chassignites and Nacklides have been linked to the same magmatic system. They have same crystallization ages, same ejection ages, etc., series of evidence that relate them to the same magmatic system. So basically, we have that the Chassignites crystallize first, and there's almost pure mantle contribution, and then the Nacklides have crystalline mantle contribution. Here I'm showing the petrologic images of Nacklides from base of the stratigraphic sequence to the top. And the two Nacklides that we studied were Northwest Africa 998, which is the one representing the base of the cumulus pile, and Nakla, which is more or less in the middle. So Northwest Africa 998 has olivine equilibration because it has the slowest cooling rate, and also blocky plagioclase in the mesostasis, etc., because it has more time. Important to point out that crystallization ages of the Nacklides span 94 plus minus 12 million years. So they are actually temporally distinct extrusive units from the same volcano. They did not crystallize at the same time at a single stratigraphic sequence, as many studies point out, and this has some implications. Okay, so the apatite grains that I studied are these ones in NACLA and Northwest Africa 998. The first two are cumulus apatites. The first one is completely embedded in pyroxene, and it's not associated with a fracture, so that gives evidence of a cumulus nature instead of intercumulus. And the FIP cut was done along the elongated axis or elongated direction. The FIP2 was extracted in an apatite grain that was closely intergrown with titanomagnetite, and it was cut perpendicular to the elongated direction, and it's also considered to be cumulus apatite. And then NACLA apatites were located inside a late stage melt pocket. And so we cut a set of different similarly oriented acicular apatite grains inside this late stage melt pocket. So first, we are going to talk about these nanostructural domains. I will only basically show high resolution images of apatites in these two NACLites and then other planetary bodies for comparison. So in first FIP section, FIP1, we show that in dark field STM images which depicts composition, we saw some domains, some models texture at the 5-10 nanometer scale, which could be corresponding to these nanostructural domains in high resolution TM images at the same scale. These differences are due to differences so this contrast, this is what we see here, these differences in contrast are due to slight misorientations of the crystals with the crystal relative to the incident beam. Okay, so it's very difficult to outline the different domains because the interfaces are blurry and are coherent, so there's continuity in the lattice planes, but we can see that there's some differences in contrast. And so also we saw that the diffraction patterns show streaking in these apatites that show the domains. FIP2 is the most interesting one because we also see these 5-10 nanometer scale domains, as we saw in FIP1, you can see. Okay, so it's basically it's due to the changes in the orientation of the crystal, and also we have these boundaries that are diffuse and the location of vacancies, but we also saw that there's undulosity in the A direction, which is a pretty interesting observation that's not observed before in any other crystal. And so if we looked at this direction, we see that the lattice fringes show undulosity, but still are continuous. The diffraction pattern also shows streaking. And so all this is indicative of strong localized elastic strain within the lattice. Is elastic because the lattice planes are still continuous. If they were not elastic, we would have developed dislocations that we do not see. So we concluded that this would be nanoscale segregation of fluorine and chlorine, also based on this model texture that we saw with dark field STM images. And that the interfaces are where vacancies are localized. With NACLA, I'm showing here the whole FIP section because it was this interstitial region where we had 4 different apatite grains. And we also saw some differences in contrast, but the domains were less apparent. So we couldn't see them as well as in Northwest Africa 998, which is consistent with apatites having crystallized very fast and also cooling down very fast. As less time, you cannot develop this subsolidus X solution. And we also saw that some apatite grains show amorphous regions that were indicative of later secondary alteration that probably were also causing the clay minerals around the fifth section. But the domains were present in some areas and they were not in others. They were highly variable. We could also learn about the microchemistry of apatite grains that you cannot see with SEM, EDS, or with microprof because these are super small. And we could see that iron, silica, rare earth elements, and fluorine were concentrated in the nucleation zone at the center, at the core of the apatite, and then the apatite were enriched in chlorine at the margins. And so the fact that we still see the preservation of this differentiation of elements means that there was no subsolidus equilibration, especially because iron equilibrates really fast comparison to rare earth elements, and we still have it preserved. So we concluded that NACLA apatites crystallize first from a melt that experienced degassing during and mechanical mixing with crustal sediments, and at first this was as open systems and all intercumulus melts were connected with each other, but as the crystallization advanced, these were closed systems, and then each apatite grain evolved differently one another. That explains the differences in composition from one apatite grain to the other, only a couple microns apart. So going back to here and also taking into account that the stronger non-ideal mixing along the fluorine-chlorine joint compared to fluoro-H or chlorine-OH, we see that Northwest Africa 998 has slow cooling and has more time to develop these sub-microstructures during subsolidus cooling, where vacancies are really key to stabilize this fluorine-chlorine within the anion channels. Whereas, I'm moving my screen again. So for fluorine-chlorine apatites, there's the creation of an additional off-mirror fluorine site that's coupled with a relaxed chlorine site, allowing sufficient fluorine-chlorine distances to maintain the solid solution. And we also have this calcium 2 site that splits in two different calciums, one for chlorine, one for fluorine. And so this was the first time that we observed this in a natural ternary apatite. And in order to have this exsolution, we need to be under 800 degrees Celsius, otherwise it's miscible. So we concluded that we were at about 600 degrees. And then for NACLA crystallizes after 95% melt solidification. And so it's a late stage mineral. Apatites grow very fast and cool quickly. They have less time to develop these microstructures. And so we have also the degassing that makes these huge differences, huge range or variation, fluorine, chlorine-rich apatites. For chlorapatites, vacancies are also very important for stabilizing them. Okay, so now here I'm showing the chlorine to fluorine ratios because it's an important parameter in also developing these microstructures, these exsolution domains. When we are closer to 1, that means when we have basically chlorine and fluorine at similar proportions, they are more difficult to stay in the structure together without doing the dislocations and staying together. So we have more chances to develop the nanometer scale domains. Also, we have some directions that we can see them better, which are the A direction. We see better this expansion and contraction of the calcium 2 triangles, which is the case of FIP2 and FIP3. And so for FIP2, we are in a very favorable favorable, I don't know the name, the pronunciation, sorry, direction to see. That's why we see these undulose lattice fringes. Maybe if we were at the 001, we couldn't see them as well. And for NACLA, we are at a chlorine to fluorine ratio higher. That's more towards chlorine-rich apatite, and so less chances to see these domains or to develop these domains. And also they cool very fast, so less time to make the exsolution phenomena. And then for comparison, if we see fluorapatite from a lunar basalt, 15058, where chlorine to fluorine ratio is just 0.15, we didn't see any nanostructural domains, because basically we have fluorapatite and maybe there's no OH and just vacancies. Then for lunar basalt 17035, we could see some differences in contrast, but still nothing to do like in Northwest Africa 998. The chlorine to fluorine ratio is also very basically fluorapatite, but it has a really high rare earth element content, which is not really well understood. What does this imply in the microstructure of apatite? And then if we see a couple of ordinary chondrites, Kendleton and Santa Barbarites and L5 and L4, they are secondary minerals. In these cases, they form by dissolution and reprecipitation and alteration of anhydrous merrillite. And so in here, we can see grain boundaries and we can see amorphous regions due to this dissolution and reprecipitation, and that it's multicrystalline. And we can also see some differences in contrast, although again, it's not as in Martian apatites. And we could see also some streaking in the diffraction pattern. And these are basically chlorapatites, really rich in chlorine, which is the critical element. Then just to finish this part, apatites from a terrestrial setting, we can see there's absolutely non-microstructures. The high resolution TM images are really uniform and beautiful and nothing. That's because if you can see the chlorine to fluorine ratios, it are basically fluorapatite pure, and so fluorine are happily into the mirror planes. Okay. Now we will move on to the discovery of a melt inclusion in Northwest African 998 apatite. This was the first melt inclusion found in an extraterrestrial apatite. So I will go over a bit of the model first to understand the implications of that. That's a very simplified model that is not correct, but just for understanding what is going on, we will assume that we have this magma chamber, where we have first the chassignites crystallizing. And here I'm showing that when late stages of crystallization of the chassignites, there was an addition of a chlorine-rich crustal component, fluid or sediment, that was added into the magma. And so this is seen in Shear et al. 2018 work, where they show that apatite in intercumulus regions from chassignites had heavy chlorine signature that was believed to come from this crustal signature, whereas apatite in melt inclusion preserved the original light chlorine isotopic signature of the mantle. And so NAClites crystallize, all the NAClites crystallize from a melt, from a magma that was already enriched in a chlorine-rich crustal component. Then Northwest Africa is the first NAClite that crystallizes, Lafayette, Gobernador Valadares, and NACLA. And as NAClites are crystallizing, the melt increases its chlorine content because it's incompatible, and eventually reaches chlorine saturation with respect to a chlorine-rich fluid vapor. And that explains the extreme fluorine-chlorine ratios that we see in NACLA apatites. And so then finally, there's fluid loss or degassing that oxidizes the residual melt, and that happens right in the end. And so this is the well, very simplified model, but so here I'm showing that chloroamphibols up to that moment were found only in late forming naclites, the mill naclites and the Northwest Africa 5790. They were found in augite and in large metal patches. And so yeah, and then in the chassignites, the amphibols were chlorine poor, were kersutite, and yeah, we had the light chlorine apatite. So so what is the source of chlorine to form chloroamphibols in these late forming naclites? In that the studies were suggesting that there were 3 different possibilities. We had an early crustal assimilation of this chlorine-rich crustal component into the whole system, and then the growing pyroxenes trap portions of the chlorine-rich melt prior to chlorine saturation, and as melt inclusions cooled, the melt reached chlorine saturation and exhaled a fluid that stabilized the formation of chlorine-rich amphibols. That could be one model. Second model, exactly the same, but the trapping of the melt is once the melt is saturated in chlorine and exhales a chlorine-rich fluid, and then this chlorine-rich fluid is trapped by the growing pyroxenes as it was degassing and formed the chlorine-rich amphibols. And the third mechanism would be assimilation of volatile-rich evaporitic sediments to the mill naclites when they were erupting, when they were intruding subsurface sediments, still at a moment where crystal melt ratio was still low to allow convection. Third model is already ruled out because these perchlorate salts, these subsurface sediments, have a chlorine signature that is not matching with the one we see we have tested. And between 1 and 2, we showed that with this new melt inclusion that we discovered in Northwest Africa 998 apatite that represents the first naclite that crystallizes, we show that there's also crystallizing chlorine-rich amphibols in there. And so we do not require to have chlorine saturation at this time because we are still very early in the crystallization sequence, and that rules out already one of the possibilities. So this melt inclusion was the first discovered in extraterrestrial apatite, but they may be relatively common. It's just that they are very small, and so we need TEM to discover them. And we also saw they were perfect euhedral, and that the diffraction pattern showed they were consisting of ferrochlorowinchita, which is a new type of amphibol in the naclites. It's a sodium-calcium amphibol that also shows some zonation. And then we also saw iron-rich low calcium pyroxene close to ferrocylite, as well as in the residual melt inclusion symplectite. If we place the amphibol in a chlorine weight percent versus A site, comparing with other chassignites and naclites, we see it's consistent with other naclites, but it has the lowest A site, but the chlorine content is similar. And so here I'm placing all the amphibols discovered to date with the new one in Northwest Africa 998. This is consistent with having a clear separation between chassignites and naclites, where chassignites are only derived from mantle melts and naclites have crustal mantle derived melts. And so there's an addition of a chlorine-rich crystal component clearly at the end of the chassinite crystallization. And so from these two models, we conclude that chlorine-rich amphiboles were able to crystallize in the whole cumulus pile. They were not limited to the top, and that they could form only with the addition of this chlorine-rich crystal component. Could be also that the Martian mantle is already rich in chlorine, and so yeah, we don't need this saturation in chlorine and this exsolution of a fluid to form them. And now we move on to the last discovery in Martian apatite, which is an epitaxial fluorapatite vein that records the late hydrothermal system, more recent in time on the geology of Mars. Secondary minerals serve to understand the interaction between groundwater and igneous rocks. The age of the alteration event that altered naglites is 633 million years, is quite recent in time. And up to date, secondary pre-terrestrial minerals in Northwest Africa 998 were only identified as minor eadingite veins in olivine. And so we discovered a nanovein within a cumulus apatite grain that helped to acquire new information on the nature of this ephemeral water-rich environment that exists in the recent past in the subsurface of Mars. The vein had a composition that was very different from anything else, also from the literature in this meteorite. We rule out the terrestrial origin. I will go over it later. We determine the potential role that hydrothermal systems played in the volatile evolution of naglites and on the planet. And we evaluate how the post-magmatic history affects the utilization of apatite to reconstruct the magmatic and volatile behavior on the Martian mantle. So this is the images of the vein. The first on top are bright field TM images, and we can see that we have an overgrowth of a phase in this vein seen by this strain contrast. We also see, well, that the host apatite is chlorine-rich fluorapatite, while this overgrowth is fluorapatite, but I will show that later. We also see that the diffraction pattern is exactly the same. So that means there's crystallographic continuity. We see in dark field STM images that there's a sharp interface between this vein and the host apatite. And we also observe nanoporosity in the vein, which is, there's two kinds of nanoporosity, smaller ones at the margins of the vein and larger ones at the center of the vein that seem to be nanotubes in 3 dimensions. And so we wanted to test the composition of this vein. It's difficult for their small sizes. And first, the image on top were performed with the GEOL 2010F, the old TEM at UNM, where I did this line profile. It was quite noisy, so I had to average 4 points each to have clear patterns and see what was going on. And it was not very clear, so when we published this paper, Adrian did new line profiles with the new GEOL new arm TEM, and he ran like 10 or 12 line profiles, and here only showing 2 of them to just show that there's this clear increase in fluorine at the margins of the vein in green that represent the fluorapatite, and then they decrease at the center of the vein. And the last image on the left, you can see that silica in red increases at the center of the vein while everything else decreases, meaning that there's another phase, a silica-rich phase at the center of the vein that was not detected before. But if you see the compositional X-ray maps, especially the one in the middle, you can see as well that the fluorine is at the margins and the silica is filling the center of the vein. So we have that from previous observations, and now we are adding high-resolution TM images to show also that there were some amorphous material intermix or in between the crystalline material in the vein, crystalline apatite, and this amorphous material is probably where silica is. And so all these observations suggest that we are seeing at an epitaxial overgrowth of a fluorapatite caused by a fluid-mediated process, a dissolution reprecipitation. So a fluorine-containing solution interacting with chlorine-rich apatite will end up chlorine-enriched, and the new apatite will be fluorine-rich. This can have important implications with fluorine-rich fluids interacting with chlorine-rich apatites. Here I'm showing finally the formation of this vein with a cartoon. First, we have opening of the cleavage planes through shock or maybe just by settling into the magma chamber. Then we have infiltration, rapid infiltration of fluid penetrating these cleavage planes, remaining as a closed system. We have dissolution of the parent chlorine-rich fluorapatite and formation of tiny pores and amorphous material. Elements exchange, there's redistribution of elements in local equilibrium with the fluid. And then we have crystallization of new fluorapatite that is in equilibrium with the fluid at the vein margin. And so the fluid gets enriched in chlorine. And finally, we have the crystallization of the SiO2-rich phase at the center of the vein with the leftovers that are last fluid filled pore spaces, which are the second type of nanopores. So finally, temperature of the vein can be estimated by taking into account an equation of the diffusion coefficients of chlorine as a function of temperature. Although Lee et al. Were considering magmatic temperatures and we are at lower temperatures, so we had to extrapolate the numbers, and that could lead to some errors, and we have to take that into account. And then we also took fixed second law of diffusion to calculate different times for chlorine diffusion as a function of temperature, and we plotted them, and we have that our vein, taking into account that it has a width of 100 nanometers, was formed by a fluid that was at a temperature of 300 degrees Celsius. So that's not a terrestrial origin because of all these reasons. First, because we have preservation of compositional differences that in such a small scale that can only be possible if we have a rapid injection of a fluid more consistent with something like chalk. The composition of the fluid is fluorine-rich instead of chlorine-rich, which is more typical of terrestrial weathering fluids. The precipitation of calcite, which has been found in other naclites, other chips of this meteorite, as a terrestrial phase, requires an alkaline fluid, which is not compatible with the acidic fluid required to dissolve apatite. Also, the temperature, 300 degrees, is too high for desert weathering fluids. And finally, we didn't see anything else as a terrestrial alteration product in our thin section or FIB section as well. And so this is this fluid recorded the same fluid as other naclites, or is a different fluid? We don't know. We just know that the fluid is a little bit different. It's chlorine pore, fluorine silica rich. So it has a different pH as in other naclites. Maybe because these naclites emplaced at different times. Maybe it's a less evolved fluid that occurred in Northwest Africa 998 that then evolves to other and dissolves mesostasis glass and then affects other naclites. Or maybe this fluid was affected at a time where Northwest Africa 998 was emplaced and not yet the others. So there could be different possibilities. Same fluid, just less evolved or a different fluid that occurred before other nuclides were placed. And now we'll move to terrestrial apatite. This is my work done in Universitat Autónoma Barcelona, where I am showing a case study for apatite in Les Guilleries. Les Guilleries is a region in Catalonia. The geologic setting is the following. We have a Paleozoic basement constituted by metamorphic and igneous rocks from Cambrian and Ordovician. And then we have intrusion of mafic igneous rock during the Hercynian Orogeny and then later there's this post-Varisc magmatism related to the Triassic extension and fragmentation of Pangea, which triggers the injection, the formation of these deep land profile dikes coming from much deeper places that cut all the above lithologies. So the land profiles that we studied are emplaced in marble, but they are also placed in granitoids and other types of rocks along the region of study. These are the two apatite grains that I will show you here because I choose these apatites that we think form first. They are primary apatites. We cut two fifth sections, one sliced perpendicular to the z-axis and one sliced parallel to the z-axis in order to learn about the 3 dimensions. As I did before, I think it's the best way to approach apatites and to have a better sense of the 3-dimension situation. So here with fib 1, we see apatite looking down the z-axis and here looking to the a-axis. Okay, you can see that, maybe you cannot see it, but I tell you that in both apatites we have a region filled with inclusions, and even we have a larger one that was that did not survive the fib preparation, but we could see them while we were preparing the fib section. And so I'm showing you here better images of these inclusions. You can see that they basically fill the core of the grain, and the interface is irregular. And then we have inclusion-free apatite rim. We don't see differences in compositions between the apatite core and the apatite rim. And here we see the inclusions. They are following the negative crystals of apatite, and they are basal, so equine sections of these inclusions. In the other fib section, in fib 2, slice we see the A to the A direction. We see that inclusions indeed are prismatic, and it's the same story. They are filling the apatite cores, and they are negative crystals, euhedral. And you can see that there's 2 phases or even maybe 3. And we don't know if they are just 1 phase, 2 phases, or none, or if all of them contains everything, but it's just a matter of the limitation of seeing 2 dimensions. So here, high resolution TM images, we were very lucky to get those because they are really difficult to get. As soon as I was imaging them or doing any sorts of analysis, they were destroyed. We found that they consist of pyrrhotite, and so we have reduced conditions because sulfur is present as sulfide. Then we have these bimodal inclusions where we have pyrrhotite and an amorphous phase, and we have others that were just amorphous. When we tried to determine the composition, we were taking this type of inclusions that include both phases, and that's when inclusions were completely destroyed. The line profiles were a bit of a disaster, but still we could have 2 of them a bit clear. where we see that there's an increase in iron and sulfur. And in the void part, which is the one that I was interested in, there was a decrease in everything. That's why at the beginning I thought maybe there's nothing, but because it's amorphous, it's more likely to be an aqueous fluid or something like that. Also, the fact that the inclusions were lost really rapidly during analysis, they went from euhedral shapes to spherical and finally disappearing, made us think that this could be more like an aqueous fluid. Then I did these X-ray compositional maps at Goethe University in Frankfurt with Sherry, and we saw that we detect silica. I didn't detect that at my university because the instrument is not as good. And in here we saw some enrichment in silica that was not exactly where the inclusions were, but surrounding them, kind of associated with them, but not in the inclusions. We saw that the silica was real. There's a clear increase in silica in some regions. And so we conclude that there was this crystallization of apatite taking some immiscible iron silica-rich melt that was trapped into negative crystals of apatite, and upon cooling, melt crystallized into pyrrhotite, and then a silica-rich aqueous fluid was exsolved, and then silica leave the inclusion. There was silica leakage towards the surrounding apatite. We also see that inclusions are connected to strain, and that this irregular interface is very interesting because that rules out that this limit or this change is due to a change in fugacity of oxygen fugacity or a change in the cooling rate, because that way we wouldn't see it irregular. We would see just following the growth, the regular growth of a crystal, right? So the fact we see this irregular interface made us conclude that we are seeing at two steps of growth in the apatite. First, we have apatite crystallizing with taking immiscible sulfur-rich melt that was trapped in these negative crystals of apatite and made these inclusions. So here's an image of that, and one thing that's very interesting to note is that these inclusions are associated with strain and also high contrast in the apatite. You can see the clear difference on the right. And then what we think that happened is that this apatite was a cumulus phase, and then it was corroded by the surrounding magma. And then when the lamprey took more contamination from the surrounding rock, like granitoids, where are full of apatites, and lamprey's they have more alanites, which this is where the rare earth elements are. But when the magma took again contamination from the adjacent granitoid, then new apatite epitaxially grow over this first apatite, and that's why we see this reaction front and the second apatite very clear without inclusions. That's because of, well, we think that's because of that. And also another evidence for this story is that in the diffraction pattern of apatite that contains the inclusions, we have these faint dots that are more or less in the middle of apatite diffraction pattern, which we think is due to this high strain in the apatite structure due to the inclusions, in contrast to the epitaxial apatite, which is inclusion-free, and the diffraction pattern is very clean. So just some final remarks for my talk. Apatite is a fascinating mineral. As more as I look at it, more I like it, because it's a surprise always. It can provide additional insights into petrogenetic histories and sources of volatiles on different planetary systems. However, apatite is very complex. It's a mineral that can result from a wide range of processes, and knowing its microstructure is essential for interpreting the volatile budget of a source. So additional work on natural apatites is needed to better understand the different solid solutions that ternary and binary apatites can make. And so also want to point out that microprofile SEM analysis cannot detect all the small variations in chemistry, like inclusions and veins that may exist in apatite, and they provide valuable information that so TM studies are needed to interpret these apatites. And this acquired knowledge will serve to better understand Artemis 3 samples and interpret the volatile budget of the moon when new samples arrive. Thank you very much for your attention. I'll be happy to take any questions.
Thank you very much, Marina. That was terrific. Before we take questions for Marina, I just want to let everyone know that next week our speaker will be Noah Petro, who will discuss the Artemis 3 mission. He is the chief scientist for that mission. So let's go ahead and take questions online. I don't see any hands raised. If I'm missing you, please just go ahead and.
Hi, Chip. This is Horton.
Yeah, Horton.
Hi. Congratulations, Marina. It was a terrific talk.
Thank you.
We're finding lots of interesting stuff, including halite in veins and also in inclusions in the rocks along the Curiosity rover traverse. I was wondering about how you can, if processes, of course, we're looking at very evolved materials that's been eroded and redeposited in sedimentary rocks. But then the question is whether we can mobilize fluids from further deep below the surface. And could apatites contribute, the breakdown of apatites contribute to releasing those fluids and providing a source for chlorine coming up, forming some of our veins and materials that we're finding in the concretions?
Yeah, I think so. I mean, I think this is a good example to test that, right? To see these apatites and see if we have evidence for fluids or for mobilization of fluids from, from surface to the interior or the other way around. So yeah, I think that's it. That's one of the examples we could do it.
Well, and I'm also excited that you will probably be able to look at the samples returned from Mars someday in the future. So something to look forward to.
Well, we'll see. We don't know. Maybe.
Thank you very much, Mark. Frank Brinker, you have a question, and thanks for attending, Frank.
Hi, Marina, fantastic talk.
Yes.
So I really enjoyed your work on these apatites. I have one question about the domains that you showed in the apatites. You mentioned that they are fluorine rich and chlorine rich. Is there a chance to see this with an EDX map, or?
Yeah, no, we couldn't see them in EDX map, but I think with eels could be a possibility. I have really bad luck. Every time I try to do eels, it's not working. But I hope that in the future I can try with eels, because eels work better with light elements, and so maybe we can map them, and see actual domains of these two elements in these domains. That's something that it really is needed to do.
Okay, perfect. Thank you.
Thank you.
Any questions in the room at UNM? Marina, I have a question. Textually, in the first part of your presentation, you were pointing out how apatites are seeming to record evolution of individual melt pockets, and sometimes different melt pockets may stay open for longer and other ones will close up. What are the implications for degassing and the impact of degassing on stable isotopes?
Well, there's, for example, there's this work on Browns et al. 2022. They show that degassing of these for open systems in these melt pockets would change the sulfur oxidation state, so would go from, I don't know, +6 to -2. So I think that we should see some changes in redox conditions in stable isotopes as well. But I don't know because I haven't done it, but for sure there has to be a record of that in this degassing history.
Yeah, I think there are several papers that have been done on lunar basalts that really illustrate, for example, the variation in chlorine and D to H within one individual sample can vary, and maybe it's primarily due to, again, different closures of these melt pockets. But that's great.
Yeah, exactly. If you close the melt pocket, then you don't see the degas anymore. And so you will have differences between you can assess the closure time, right, between different melt pockets.
Fantastic.
Or the relative time, at least. Yeah.
Any other questions from the audience at UNM?
Good talk.
Good talk. And any more questions from the audience online? No, I guess not. So let's go ahead and we'll end the seminar. And I just again want to thank Marina again for giving us an update on her work on examining the microstructure of apatite and its implication for apatite as a recorder of volatile processes and volatile characteristics of magmas. Marina, again, thank you so much. And it's so nice to see you.
Thank you very much. Thanks to you.